All right, hey you guys, and welcome back to another AP Physics C, Electricity and Magnetism, not E&M. Today's gonna be sorry, yes, E&M, not mechanics this time. Normally we would have the mechanics here, but I felt like doing E&M today, so we're gonna do E&M. So let's just hop right into it. Um, and we're starting with the 2021 because I would do the 2024, but I'm not because I can't explain it that well and I have to figure it out more. But I feel like I can do this one, so why don't we go ahead and start this? So the circuit above is composed of an ideal 10-volt battery, three resistors, right? Three resistors and three capacitors. So here, oh, and three capacitors. Ignore that, right? With the values shown, an open switch S, oh, and an open switch S. So this is open. The capacitors are initially uncharged, and switch S is now closed. Calculate the value through R1 of current through R1 immediately after the switch is closed. Okay, so what they want us to realize here, right, is let's think about when the switch is closed, current is going to start flowing this way, right, because that's the only path it can take. Now, you might think, oh, okay, current branches, right, because Kirchhoff's junction rule. No, it won't do that because current usually tends to take the path of least resistance. And when you have capacitors, immediately after the switch is closed, the capacitors will act as bare wires, right? So if I were to redraw this, no, this is just a bare wire, right? There's no resistance across those. So the electrons, the current, will tend to flow through the capacitors immediately after the switch is closed and bypass these two resistors entirely. So the statement that we're going to make, we're going to say the equivalent resistance is just 100 ohms. That's the resistance of the entire circuit because these ideal capacitors don't have resistance, right? If they were non-ideal, that would be a different story. But these capacitors have no resistance. So the equivalent resistance is just the resistance of R1. Now we need to think Kirchhoff's loop rule, right? The voltage of the battery, I'm going to call it EMF, the electromotive force, minus, right? Because this is a positive potential difference. Now resistors will do work against the current, so that's going to be minus the voltage across R1, right? Has to be equal to 0. And you might be asking, well, why didn't you do the voltage across these three capacitors, right? Why didn't you do Q over CEQ or something equals delta V? The reason why I didn't do that is because immediately after the switch is closed, Q is 0. Charge has not had enough time to accumulate, right? So then I can just say Kirchhoff's loop rule, it's 0, right? Because the loop from here to here, here to here, these two are basically the only circuit components that have a voltage. So we know that the voltage across the resistor is IR, and the voltage of the battery was 10 volts, right? Well, now I can solve for I because this is just an equation. So 10 volts has to equal I, and R1 was 100 ohms. Or, well, you could say, I said R1, but you could say REQ, right? Because I stated REQ earlier. This is a general thing, the voltage, the equivalent resistance. So now, 100 ohms, that means 10 volts divided by 100 ohms will give me my current, which is equal to 0.1 amperes. Now I could consult Desmos for that, and I actually will. So there's 0.10 or 0.1 amperes. Bam. Because the current across R1 is the current across the entire resistor because resistors, the equivalent current is the current of any resistor that's in series. Right, that's just how circuits work. Next question. Switch S has been closed for a long time and the circuit has reached a steady state. And if you guys had any questions about like what I just explained, please let me know. I would be happy to answer them. So the circuit has reached a steady state. So now we're going to be tested on steady state conditions. Calculate the potential difference across R1. So now this is a different question. When it's in steady state conditions, these capacitors have all the charge they want. And I'm going to say that positive charge accumulated this way because the conventional current travels this way, and we say conventional current is how the protons would flow. Technically, electrons are flowing this way, right? But conventional current, the protons don't move, but this is just what we say because it makes math easier, would go this way, and positive charge would accumulate here, making the positive charge accumulate there, and then more positive charge there, right? So this would get plus plus minus minus. So now, after it's reached steady state conditions, these are full. They don't want any more protons or electrons, right? They don't want any more charge. So capacitors, once steady state has been reached, they act like brakes in the circuit, right? They cut off the circuit. They act like open switches. So if you take this switch and I move that over here, that's basically what these are doing now in steady state. So now the only loop I have to consider in my Kirchhoff's loop rule, which is what I'm about to apply, is the loop through here. And you might be asking, hey, why did you draw it? Why, excuse my voice crack. Why did you draw it down the middle? It's because I'm going to combine these two resistors, right, into an equivalent resistance. Because I could go through the branching of the current and say I1 plus I2. No, I'm not going to do all that. I need time on this exam. So we're going to do it the faster way. And as a matter of fact, we're going to combine all three of these resistors, say that these two, sorry, I'll say all three. So all these two resistors into one resistor that I'm going to call what R23, and say that R23 is in series with R1. So I can add up R1 plus R23 to get the equivalent resistance and then use Ohm's law, right? Or Kirchhoff's loop rule. Ohm's law is technically Kirchhoff's. It's the same idea. It's the same idea. So basically, what College Board wants you to say is that these are open switches. I don't have to think about these, right? They're not a part of the loop because current can't flow through an open switch because it needs a path. It needs a path. Current needs a path, like a conductor. So we're going to find the equivalent resistance of 2, 3, right? So what is the equivalent resistance across two resistors in parallel? Well, on the equation sheet, you'll see that the resistance of two resistors that are in parallel is the sum of 1 over R, where Ri, which is like each resistor that's in parallel, you do 1 over the resistance, add them all up, raise that to the -1, and that will get you this number. But this is the official like law that you have to know. This is how I'm going to write it, and then I'll show you the steps at the end, right? So what was the first resistance? I have a bad memory. It was 30 ohms and 60 ohms. So let's just do that. So 1 over 30 plus 1 over 60 has to equal 1 over the resistance of both of them together. So now I'll simplify this a bit. I'll get 2 over 60 plus 1 over 60. And you might be saying, well, how did you get 2 over 60? Multiply by 2 on both sides, right? And this will give me 3 over 60, and that's equal to 1 over R23, which is the equivalent resistance of that parallel branch. Now, how do I just get to this number? Because I don't want 1 over R23. No, I want R23. Raise this entire thing, or well, flip. You could basically just flip both of these fractions, right? R23 equals 60 divided by 3. 60 divided by 3 is 20. So R23 is 20 ohms. Done. Bam. So now I have this R23 here, and I'm going to visualize the new circuit that I basically just imagined. So our new circuit looks kind of like this, right? And this is a very simple circuit. Here's R1 and here's R23. You'll just realize here's the 10-volt battery. Hey, these two are in series. So the resistance, the equivalent resistance of capacitors that are in series, right, is equal to the sum of the resistors that are in series, which is, it was 100 ohms plus what we just calculated, 20 ohms, giving us 120 ohms. So that's the equivalent resistance, right? And you might be asking, hey, why are you doing all of this to get the potential difference, right? We're getting there. First, we need the current that's coming out of this battery going through here, because if we have the current by Ohm's law, V equals IR, if we know R1, all we need is the current of this, the equivalent, you could say equivalent current, to get the voltage across R1. This is the fastest way to do it, I promise you. So bear with me. So now I have 120 ohms as the equivalent resistance of the whole circuit. So now I can use Ohm's law once, right? So the voltage of the entire circuit, I'll call that voltage total, or well, VEMF, same thing, has to equal the current of the entire circuit, right, times the resistance of the entire circuit, REQ. So I know the voltage of the battery was 10 volts divided by 120 ohms gives me how many amperes? 0.8. Oh, well, I'll just write it like this. 0.08, 833 amperes. Great. Now I have the current that is flowing through this battery and flowing through here. That is not the current of these two, right? Because Kirchhoff's junction rule, whatever goes in must come out, right? It'll branch here giving us I1 and it'll branch here giving us I2, but we're not going to do that. As I said earlier, that's too much work. We're just going to keep combining things and pushing through these questions, right? So now 0.833 amperes has to equal I R1. That's the current going through our R1. We're going to apply Ohm's law again. Now the voltage of R1 has to equal the current going through R1 times, well, R1. So let's go ahead and do that. 0.833 amperes times 100, just 100 ohms. And without needing to do any math, we could do the math and just multiply in decimals. That's roughly 8.33 volts. Done. That's the voltage across R1. That's what we need. And now you might be thinking, hey, didn't you just say that how can this current and this current be the same? That's just how it works in this class, right? The current going through the battery is the current going through all of the resistors in series. So technically, the current going through R2 and R3, or sorry, R23, the equivalent R23, would be 0.833, but this one will have less than 0.833 and less than 0.833 because of Kirchhoff's junction rule. But basically, the current of the whole circuit is the current of whatever the circuit elements that are in series. That sounds weird, but you get the point. If you need me to explain it further, I'd be happy to. So let's move on. Calculate the charge stored on the positive plate of capacitor C2. This question is a little bit more tricky. So I'm going to draw these lines so I have more room to work with. Okay. So the charge stored across C2. Now you might be asking, well, how do we do this question? I'm going to tell you how we do this question. So the way we do this question is we need to realize this is a closed loop. The voltage across these 2 points, right, when I get from point A to point B, assuming this is A and B, right? That's how Kirchhoff's loop rule works. When you go from the same point to the same point and you go through a loop, the voltage has to be 0. So I'm going to apply my Kirchhoff's loop rule one time for the first time. So the delta V EMF minus the delta V of R1 minus the delta V of R23 has to equal 0. You're like, where did you get that loop rule from? And I'm going to draw out the circuit so we can visualize it, right? Actually, wait, I just drew it earlier. Why don't I just use that one? So we're going to use this circuit. So this branch technically extends over here to these capacitors that I have, right? And as a guideline for this class, the voltage of circuit elements that are in parallel is the same, right? So if these two combined have a voltage of like, say, 8 volts, this is just saying, like, I'm just randomly making something up. That voltage has to be the same as these two. These two have to have it. Well, these two combined have to have 8 volts, right? And then C3 also has to have 8 volts because the voltage of things that are in parallel has to be the same. That's how this class works. That's how circuitry works, right? So let's move on. And now we're going to figure out what R23 is, right? So we knew it was 10 volts from the battery minus, and we figured this out earlier, 8.33 volts from R1 has to equal, now where did I get the equals? I just added VR23 to both sides so I can solve for it. Has to equal delta VR23, which is roughly equal to 10, let's do this on decimals, 1.667 volts. So now I know that these two together, right, combined, if I combine their resistors into an equivalent resistance, which I did, have 1.667 volts, meaning these two, if I combine them into an equivalent capacitor, have 1.667 volts. This one itself has 1.667 volts. Great. Now I can use the voltage to find C2. So now let's think. The voltage across C1 and C2, if I make them into an equivalent capacitor, is not necessarily the voltage of the individual ones, right? Because we know that capacitors in series, when they're hooked up to a battery, right, they have the same charge, but they don't have the same voltage. But if the capacitors are hooked up to the same battery and they're in parallel, they have the same voltage, like I stated earlier. So we're going to combine C1 and C2 into a single capacitor. And I know that capacitor has to have the voltage of 1.667 because there's no other circuit element there to cause the voltage drop, right? Oh, I lost my train of thought. And using that, since I know capacitors that are connected to a battery in series have to have the same charge, the equivalent capacitor's charge has to equal the charge of the individual capacitors. So now I'm going to use the fact that I know 1.667 volts is equal to delta V R23 and say, oh my gosh, and say that has to be equal to delta V C12. What is C12? Well, let's think. Capacitors in series follow this rule. 1 over CEQ equals sum of 1 over C of the individual capacitances. Like the resistors that's in parallel, if you have resistors in parallel, you treat them like this. If you have capacitors in series, you treat them like this. So they kind of opposites, but general idea is the same. So the first capacitor had 10 microfarads. The other capacitor has 15 microfarads. So if I take 1 over 10, and I'm not actually going to do the math, I'm going to let Desmos do it. 1 over 15 microfarads, and raise that to the -1, that has to give me our equivalent capacitance, right? Hold on, I think I might have... Nope, I didn't. That has to give us our equivalent capacitance here. So let's figure out what that is, because if I raise something to the -1 like this, it'll give me just CEQ over 1, because I'm just raising to the -1 just flips fractions. That's what I'm doing here. So let's do 1/10 plus 1/15. Raise the whole thing to -1. 6 microfarads. There we go. That's the equivalent capacitance across this branch. And now that I've combined them, I can say safely that the voltage has to equal 1.667 because it's in parallel with the other ones. So the voltage has to be the same. So let's go ahead and use that fact. So now, by Q equals C delta V, the charge that's on the big capacitor that I just visualized, right? When I'll just visualize it like this more so. The big capacitor, like this. Here's R1, here's R23, and here's the capacitor that I just merged, C12, using, well, physics. Here's 3. These all have to have the same voltage. Q on 12, right, has to equal C12 times delta V12. I know delta V12 is 1.667 volts. And I know that C12 was 6 microfarads. So if I multiply 1.667, that means the charge has to be roughly 10 microcoulombs. Now that's the charge stored on this big capacitor here, that when I take the two and I get their equivalent capacitances. But I know that these two have to have the same charge stored on them if they're in series. That's just how physics works. That's a property that you should have learned in class by now if you're taking E&M. So now you know. If you didn't know, now you know. The charge on capacitors that are in series when they are connected to a battery, and only when they're connected to a battery, is, right, the same. Well, if they're not connected, there's some other special circumstances that you could see on an MCQ, but you'll figure that out, I'm sure, right? So when capacitors are in series, they have the same charge. So I'll use that fact and say, which has to equal Q1, right? Which has to equal Q2, which has to equal Q12. Done. 10 microcoulombs. Bam. There we go. So let's see. Is the charge stored on capacitor 3, or capacitor C3, greater than, less than, or equal to the charge stored on capacitor C2? Ignore that. Okay. Did I forget anything else here? Okay. So now they're asking us, this C3 here, does it have more charge or less charge than that one? Now let's think about it logically. These two, like I said earlier, have to share the 1.66 volts that they're given. But this one does not, because it only has a single capacitor in its, what's it called? In its branch. So if they have to share the voltage, that means C2 has to have a voltage that's less than C3 because C3 is 1.667. This one has to share the 1.667, therefore it has to be less than 1.667. Even by a tiny margin, it has to be less than it, right? But its capacitance is also less than C3, right? Because 20 is less than 15. So now we're going to put that into words. We're going to say greater than. We're going to say by Q equals C CV, since delta V equals 1.667 and C2 share 0.667. Well, what I should say is since delta V C3 is equal to, I should just move this whole thing over. Oh, I should just move this whole thing over. Since delta VC3 equals delta VC12, which is equal to, and C2, okay. So since the voltage across C3 has to equal the voltage across C2 because they're in parallel, since in parallel, right? And C2 has to share its 1.66 volts with C1, delta VC2 has to be less than delta VC3. And since C2 is less than C3, right? 15 is less than 20. Therefore, we'll just write Q3 has to be greater than Q2. Bam. Does that make sense, right? Because if I have more capacitance and I even have more voltage, that'll just make Q go up a lot. And there we can leave that there. Switch S is then opened. Okay. So after switch S is opened, right now there's a break in the circuit, but these capacitors have been charged. And they each have their charge on them. Determine the current through R1 immediately after the switch is opened. So when the switch is opened, these have accumulated positive charge on their top plates, right? As I explained earlier. So I'm not going to re-explain it. So current's going to get sent this way, right? Because conventional current flows from positive to negative. And let's think, can there even be current going through R1? Let's think, if it goes through here, there's a break in the switch. The current has no path. Therefore, there has to be no current going through R1 because it can't complete the path. But instead, the current will go this way. It'll bypass R1, right? So earlier, these two were being bypassed. Now this one's being bypassed. So we're going to say IR1 equals 0. No path / closed loop includes R1. Done. Calculate the current through R2 immediately after the switch is opened. So let's think about this new circuit that we've just created with the switch open. So after the switch opens, like we just said, there's no path on this side. We can't even think about having a path on this side. And the battery even, if I go all the way on the outside, right, it can't even finish. It has to come back through at the switch S. So this entire circuit is obsolete. We don't have to think about that because the switch has been closed. It's been taken out. So, sorry, this thingy. These two resistors are still good, but this is out, right? So let's think about this new circuit that we've made. So it looks kind of like this, right? It looks like this, and we have this other resistor, and we have these capacitors in series, and we have this one capacitor. And you might be thinking, hey, this looks like just a really glorified RC circuit. What if I just combine these two like we did earlier and combine these? Well, then you get a circuit that looks kind of like this, and I'll label these. And, oh, that's a resistor. Oops. And now I want you guys to think. The voltage across each of these branches had to be 1.667 because circuit elements in parallel all have 1.667 volts. right? And it doesn't matter when I combine them into their equivalents, they will still have 1.667 volts, right? So let's think. I have this new capacitor C123. I don't even need to calculate the capacitance because I know the voltage that it has, right? There was plus here, minus here. Let's think. Current will flow like this. And by Kirchhoff's loop rule, all the current has to, or all the voltage has to drop there in order to complete the loop. So let's write delta VC minus delta V R23 has to equal 0. So if delta VC was 1.667, and you might be asking, well, if the switch opened, wouldn't the voltage change? The reason it doesn't is because it says immediately after. Charge has not had enough time to move yet. It didn't even move yet because it said immediately after. So Q would have been the same and C would have been the same, meaning delta V would be the same. So now we're going to say, since these two will have the same voltage, right, equals delta V R23. And since R2 and R3 are in parallel, I can essentially say delta V R23 has to equal delta V R2 and delta V R3, right? And that's the same thing that we did earlier. This voltage has to equal this voltage, which has to equal this voltage. Things that are in parallel will have the same voltage. I'll just keep repeating that, right? So now I can use Ohm's law and say, well, if this R2 was equal to R23, and I said R23 is 1.667 volts, I can say 1.667 volts is equal to, well, the current going through R2 times R2. And what was R2? I forget, so we're going to go look back at it. It's 30 ohms. So let's go ahead and see. Where's 30 ohms? It's going to be 1.667 volts divided by 30 ohms. Oops. To get us to our current. Let's do that on Desmos, which is roughly 0.055667. There's another 5 here. Amperes. Done. That's all you need to do, right? You use Ohm's law and you say the potential difference to R2 is equal to the potential difference across the capacitors before the switch was opened, right? So there we go. We'll leave that like that. So on the axis below, sketch a graph of the potential difference V across capacitor C2 as a function of time t if switch S was opened at time t equals 0. Label the maximum value. Okay. So the voltage across capacitor C2 was what? What did we say it was earlier? It was, where's C2? I don't really have to care what it is actually. Because if I just think about it, we knew the charge that was on C2. What was the charge that was on C2? Okay, we knew the charge that was on C2. And we knew the voltage, and we knew the capacitance of C2. So the charge that was on C2 was 10 microcoulombs, right? As we saw for earlier. And C2 is 15 microfarads, meaning the potential difference is 2/3 of a volt. So we'll just label the max here to be 2/3 of a volt, right? And now we have to think about RC circuits. This is going to keep giving off its charge, and the resistors are going to keep restricting the flow of charge to a point where charge isn't moving anymore, because it'll just keep doing work on charges to have them move, to have them have velocity, and the resistors will just keep reducing the velocity of those charges until it reaches 0, until there's no more charge left to push out. So, like an RC circuit, as is customary with RC circuits, this will concave up and slide down because it has to approach 0. It can't be concave down because otherwise, I'll just visualize it for you, it wouldn't be approaching 0, right? The voltage would actually be approaching a negative number, and we don't know that's not what voltage is approaching. So here's 2/3 volts, 2/3 of a volt, and that's your graph, right? This is just you can go look up RC circuits voltage graphs, and that's what it looks like, right? So now let's think. Capacitor C3 is replaced by two 10 microfarad capacitors connected in series. Switch S is closed, and the circuit reaches equilibrium. Switch S is then opened at times t equals 0. For t is greater than 0, with a sketch of the graph of the new voltage oops, will the sketch of the graph of the new voltage across C2 as a function of time be above, below, or the same as the graph sketch for part C? So if this was replaced by two 10 microfarad capacitors, right? Let's just visualize that. It would look something like this. Here's 10, here's 10. Then the actual equivalent capacitance would actually go down because it follows that 1 over C law. And we know by just physics, it'll just capacitors in series will reduce the overall capacitance. So we're going to use the time constant to justify this. So I'll say below, right? C3, I'll say in the C3 branch, CEQ is now less as capacitors in is now less. Is now less. We don't even have to say it, right? CEQ is now less. Therefore, CEQ of the whole RC circuit would be less. Therefore, tau, the time constant, we'll say since tau equals RC, tau decreases if C decreases, right? Therefore, the capacitor will discharge, the capacitors will discharge more rapidly, and the new curve would would be below the old curve. So what I want you guys to think about, that's a really explanation, and it's from College Board. So what I want you guys to think about is like, here's that branch, the equivalent branch, and here's my capacitors now with the in series capacitor, right? If I combine all of those, they become an RC circuit that just kind of looks like this. And this has a time constant tau. You know that tau, it's in the RC circuit, it looks like this, T to the negative tau. And the voltage when you're discharging is actually this equation. So let's say V naught of the whole thing, it was 1.667, right? Times E to the negative 5. Let's call tau initially 5 over X. Let's look at that graph. What the flip? Oh, it's T over tau. Sorry. It's T over tau, not tau over T. And if you'd like to see the derivation, I'm sure it'll be in one of the other videos. But I'm not going to go through it today unless they ask us, which I know they won't. So it looks like this, right? But if I were to decrease tau, it decays a lot quicker, right? But if the y-intercept were to still be the same, the graph would be below the other one. So now I don't even need to consider it. I'll actually just plot the two graphs side by side so you can see, right? This other graph will be with tau, being bigger. And just look, right? The curve looks like that. It decays slower. But this one will always be below that graph because its tau will cause it to decay quicker. So I'll leave that like that. There we go. So students perform an experiment. Oh, now we're on question 2. Students perform an experiment to study the force between two charged objects using the apparatus shown above, which contains two identical conducting spheres. The upper sphere is attached to an insulating string, which can be used to which can be used to move the sphere downward. The lower sphere sits on an insulating rod, which is on an electronic balance. The electronic balance is zeroed before the lowering sphere, before the insulating rod and lower sphere are in place. Okay, so before this rod gets on there and this sphere gets on there, the balance is zeroed. So let's think about this. For the first trial, a charge of Q is placed on each sphere. So each sphere has charge Q, and the upper sphere is slowly moved downward. The students measure the distance d between the centers and the magnitude of F that appears on the electronic balance. The recorded data are shown on the graph of F as a function of 1 over d squared as shown below. Draw a line of best fit to represent the points of data shown. All right, we've done this like a million times. All we're going to do is line up our ruler as best as we can. That's good enough. There's my line of best fit. That is a horrible line of best fit. I'm doing that again. This one's better. Way better. I like that one better. All right, there we go. There's my line of best fit. Done. Use the graph to calculate the charge Q. Okay, so what they want us to realize here is that since these two charge, right, since these two spheres are charged, they have the electric force between them. When you bring, what's it called? There's static between your hair. The reason why the balloon sticks to your hair is because of the electric force, right? Positives and negatives attract, right? Like in chemistry. So I assume you all know the electric force by Coulomb's law. So here's Coulomb's law. And we're going to use it. K, Q1, Q2 over R squared. Now, in this situation, both of the charges had the same charge. So I'm just going to say Q squared. And D is the distance between the two, which would be D squared. So now the electric force is actually the force that the sphere or the scale is measuring, right? Because the electronic balance measures the force. So we're going to say F is equal to KQ squared times 1 over D squared. And now this is starting to look like Y equals MX plus B, where B should be 0 because there is no y-intercept in the Coulomb's law equation. There's no plus. It's just multiplying things. So now we're going to pick points from the data in order to find Q. And you're like, well, why are you picking points from the data? AP Physics C always does this. In linearization, you're always going to have to draw your own graph. In the new exams, draw your own graph, scale it yourself, right? Calculate your new linearized data, plot your new linearized data, draw the line of best fit, pick data points, and find some value. So it's always a picking data points thing. So I always do that, even if I don't know what it's asking me. So I'm going to pick this one. This is a good ballpark. So here's 30, comma, because in the middle of 40 and 20, there's 30, 30, comma, 10,000. And remember, this is in micronewtons. So we have to keep that in mind. Let's pick another easy data point. Bam, right here. And that is what's in between 12 and 3. That's 12,000. Is that 12,000? Yeah, 12,500. Actually, I'll just write 12,500. Move that entire thing over here. And that intersected at 85. So there's our data points. And I'm going to realize that since this is in y equals mx plus b, because this is the dependent variable, this is the independent variable, this is the slope. So we're going to write our boundary. We're going to write our statement. KQ squared has to equal slope. Now slope, or actually, yeah, slope has to equal the change in force over the change in d to the negative 2, which is just 1 over d squared. So what was our slope as well? What is our slope? It's 12, right? Rise, the change in y between these 2 points over the change in x. And we said 85 minus 30. There we go. So let's do that in Desmos. 12,500 minus 10,000. Oh, forgot a key point here. I said it's in micronewtons earlier. So we're going to write 10 to the negative 6 times 10 to the negative 6 so that we don't mess this up. Always account for your micronewtons if you see them, because micro is 10 to the negative 6 times 10 raised to the negative 6. So there's that, and divide that by the change in x, which 85 minus 30, I don't feel like doing that in my head, is roughly equal to, the slope is roughly equal to 0.1234. 454. Great. Earlier we said KQ squared equals slope. That means Q has to equal slope divided by K and the square root. Take the square root. Because I would have just divided by divided by K and then taken the square root to get of both sides to get Q by itself. So now I'm going to plug in my values. I'm going to get 0.0001 0.0454 divided by, and the Coulomb's law constant is 9 times 10 to the ninth. Take the square root of that on Desmos, 0.000454 divided by 9 times 10 raised to the ninth, and I take the square root of that by raising it to the raising it to 1/2, and I get roughly 71 nanocoulombs. You might be saying, how'd you get that from that? Well, 7.1 times 10 to the negative 8 coulombs, right? If I were to just divide by the nano, right? If this is nano, this is what I need for nano, right? I need 10 to the ninth for nano. Well, that would give me 71 nanocoulombs. Or you could just say 7.1 times 10 to the negative 8 coulombs. That's just a sign. What I did is just a scientific notation thing. It's easier to do that. And College Board would accept it either way, I'm sure. So let's go ahead and answer the next question. On the graph of the previous page, draw a circle around the data point that was taken when the distance between the centers of the spheres was the least. Now, this is going to be a little bit more difficult. So they want to pick one of these 5 data points that they want us to pick that to one of these 5 data points, and we have to think, okay, 1 over d squared. Whenever 1 over d squared is less, is not necessarily when the distance itself is less, because we'll think 1 over d squared, if I increase the distance, 1 over d squared will approach 0, right? So this is actually when distance is the most. So when 1 over d squared is smaller, the distance, or sorry, when 1 over d squared itself, the entire term, is bigger, right? D has to be smaller. So this data point is actually this one at 82.5, right? So that is when the distance is the smallest, because if you have a bigger 1 over d squared, you have a smaller distance, right? It's like the same thing here. If I have 1/3, right, and that's equal to, that's 0.333. Let's say it was 3 meters, but if I have 1 over 0.00001, decimal is 1 over 0.0001, that gives me a really big number. So this is a smaller number, but this is a bigger number, meaning that if this is a bigger number, then this number has to be the smallest distance. That is really confusing, but this is just proportions, right? If you'd like for me to explain it, I'll do it for sure. Like, just ask me. So determine the distance between the spheres for the data point indicated above. Okay, so if it was at 82.5, has to equal 1 over d squared at that point, then d squared has to equal 1 over 82.5. And take the square root. Oh, well, d equals the square root. Oh my gosh. 1 over 82.5. Let's do that in Desmos. Raise that to the 1/2 for square root. And the distance is roughly 0.11 meters. Done. What physical quantity does the vertical intercept represent? Now you might be asking, Coulomb's law has no plus. Why would it have a vertical intercept? That's where the error comes in, right? That's where the error comes in. So let's think. Because it says zeroed before the lower sphere and insulating rod were given, or will put in place, right? When I put them on there, the scale will start reading something. And what will that be reading? The force of gravity. There's no other forces acting on it besides the force of gravity. So we're going to say the weight of, because the weight is the force of gravity, of the rod and sphere. When 1 over d squared equals 0, d is approaching infinity. And that makes sense, right? Because the limit as d approaches infinity of 1 over d squared is 1 over infinity, which is 0, right? D is approaching infinity. Therefore, Fe is also approaching infinity, or approaching 0, sorry, as I could have just said that. All right, we'll do this better. We'll do this better. So at vert intercept 1 over d squared equals 0, and therefore FE equals 0. Because the FE is directly proportional to 1 over d squared. So if this whole 1 over d squared is 0, then FE is 0. Right? Therefore, the only other that acts upon the objects and that would be measured, excuse my handwriting, be measured is FG. Yeah, my handwriting's really sloppy, excuse me, you guys. So the experiment is extended by collecting additional data points, which appear on the right side of the graph shown above. The new data points do not follow the linear pattern seen with the first points. The group of students tries to explain this discrepancy. One student suspects that the charge is slowly leaking off the top sphere. Could this explain the discrepancy? And the answer is yes, it can explain the discrepancy, right? Because if charge is leaking off the top sphere, the electric force has to get weaker, right? So let's think about it. If Q is leaking off of the top sphere, Fe weakens. But if distance increases, or if distance decreases, Fe strengthens. These effects, right? These effects could cancel each other out to make Fe constant as 1 over d squared increases, as seen in the graph. So I'll just go over it one more time, right? So Coulomb's law is like this: KQ1, Q2 over d squared. If the distance is continually getting smaller as you bring the spheres closer together, right? But this one increases, right? So if I have 2 over 5, right? And I change it to 2 over 1, correct? But that'll give me, this is a small number. This is like 0.4 or something, but this one's a bigger number. It's like 2. But if I account for the change by making something in the top smaller, right, then it suddenly becomes the same as it was before. It stays constant because the effects cancel each other out. If this one decreases, this one, sorry, not increases up here. If this one decreases and this one decreases, this one basically stays constant. So I can just leave that like that. Next question. A second student suspects that the excess charges have rearranged themselves, polarizing the spheres because they're conducting. That's possible. On the circles representing the spheres below, use a single plus sign on each sphere to represent the locations of highest concentration of excess positive charges. So let's think about it. As we bring those positive charges together, what will they want to do? They'll want to repel as far as possible, right? The excess charges will want to repel and will be able to actually, and the excess charges will want to repel and can move freely, conductors, because they're conductors, to the edges, a result of the repulsive electric, right, force. And it says it can also be responsible for the discrepancy. Well, how this rearrangement. Therefore, decreasing the electric force as D increases due to the rearrangement. Right? Making Fe constant. Well, making F reading, the reading of the force, constant. So there we go. Right? Because if they repel and these charges move over here, the electric force will weaken. And if the electric force weakens but distance is still increasing, then distance is still decreasing, but this distance between the two repulsive thingies or the two protons is more than it was before, then the reading on the scale will be the same, right? Because it's basically just adjusting so that it will be constant. If that's a bad explanation, I'll actually do it again. These two will repel to the edge, making their distance bigger. But the distance between the centers will continue to decrease, right? So if that keeps decreasing, kq q over d squared, what will be read is that the electric force should be increasing, but it's actually going to stay constant, right? Because the charges are moving farther and farther away, right? It'll just do that. It's a really bad explanation. The charges, since they're able to move freely on the conductor to the edges, they'll have a repulsive electric force, right? Until they're as far apart as possible. The repelling force will decrease and kind of start to zero out like you see here. And the scale reading will also, I guess you could say, start to zero out. So a third student suggests that the experiment can be modified so that the top sphere is given a negative charge that is equal in magnitude to the positive charge of the bottom sphere. So on the circles, use a single plus sign on the bottom sphere to represent the location of highest concentration of excess positive, and then use a negative on the top. We get the idea. So negative on the top, positive on the bottom. Opposite charges attract. They won't repel. They won't repel like the other ones. They'll attract. So they'll be as close as possible because the electric force that pulls them together will just keep pulling them together until they can't be pulled together no more. Right? Because charge can't hop through the air. It'll just stay on the conductor unless you touch them together. That's a different thing. Please tell me if you'd like me to explain this part. I would love to because I really just explained it badly. But yeah. If it made sense, I hope it made sense. So for a separation distance that's equal to the data point indicated in part AII, with the magnitude of the force reading, so for that point here. So for the distance that's here, would the magnitude of the force reading with the spheres of opposite charges be greater than, less than, or equal to the magnitude of the force reading with the spheres of same charges? It's actually going to be less than. Because if we think about it, here's the scale, and here's positive charge over here, and here's negative charge. And before, it looked kind of like this, where this was a positive charge. This one was pushing into the plate, right? And its weight was working with it. But now this one's pulling out of the plate, and the weight is working against it. So I'll justify. So before, Fe and Fg were in the same direction. Oh, same direction. Now they are in opposite directions. But with the same magnitude or magnitude as before. Therefore, F net, which is the F red, decreases, right? Because they're working against each other instead of working with each other. A thin conducting ring of area, oh, this is question 3. A thin conducting ring of area A, resistance R, is aligned in a uniform magnetic field directed to the right and perpendicular to the plane of the ring shown. At time t equals 0, the magnitude of the magnetic field in the ring is B naught. At time t equals 1, the magnitude of the magnetic field begins to decrease according to the equation B of t equals B over t, where t has a magnitude of Tesla seconds. Okay, derive an equation for the magnitude of the induced current as a function of time for t is greater than 1 second. Express your answers in terms of these. Okay, so now we're going to have to consider Faraday's law. Whenever we have induced current, we should be thinking Faraday's law. So Faraday's law says that the electromotive force that's induced, well, the magnitude, is the negative derivative of flux, right? So long as flux is changing. So let's think, is flux changing? Well, what's the equation for flux as a function of time if we're going to take its derivative? Well, flux is the magnetic field as a function of time in this situation, because that's the one that's changing, times the area, which is constant. So we don't have to say A of t, we'll just say A, times the cosine of the angle between them, right? Because flux is a dot product, not a cross product. So the cosine of the angle between them, you can see here, the area vector is pointing out this way. If we just imagine this area, the area vector is pointing out that way, and the magnetic field is pointing out that way. So they have a theta of 0. So cosine theta, cos 0 equals 1. So this will go to 1. So now I can say that the magnetic flux is equal to B over T when I'm subbing in my B of T equation that they gave us earlier, BA over T. So now I'll take the derivative. So the negative absolute value, the absolute value of the negative derivative of BT of this bat, I guess you could say, this is what we had earlier, is equal to, I'll just pull out my constants, it's BA, it's absolute value of negative BA, d of dt of 1 over t, which will give me, after I take out the sign and everything, it'll give me BA over t squared. And the reason why is because the derivative of t to the negative 1, I'll use the power rule. I'll move the negative 1, right? And then subtract t minus 1. Right, there we go. And that gives me negative 1 over t squared. And you might be saying, where'd the negative 1 go? Well, absolute value cancels it out. Bam, we get this equation. So there's the E induced as a function of time. There's the magnitude. Now we'll use Ohm's law to find the induced current. Because we have a voltage, we have a resistance. So I'll say E of t divided by R equals I of t. So therefore, I of t has to equal BA RT squared. Bart squared. No, but I hope that wasn't too quick, but that's basically what you have to do, right? Because it says it has a resistance R, and we have to take that into account to find the induced current. So yeah, basically that's what it goes through this. When we have the induced voltage as a function of time, and we can divide by the resistance to get the induced current as a function of time. Please let me know if that didn't make any sense or if you need me to explain it again, but I think I did pretty fine on that. So let's move on to the next one. Assume these numbers. A equals 0.5 meters squared, R equals 2 ohms, and B equals 0.5 Tesla seconds. calculate the electrical energy dissipated from the ring from t equals 1 to t equals 2 seconds. What we need to realize is power is the derivative of energy, dE dt, right? So it's how much energy I lose or dissipate. It's the change in energy over the change in time. So if I take power times the change in time, that has to equal my change in energy, right? And I know that E dissipated has to equal the change in energy. But now I'm going to introduce calculus to this, right? Because if P equals dE dt, then if I have P as a function of T dt, it has to equal dE. Here's my differential equation. I'm going to solve this differential equation. It's not really solving, it's just kind of doing. And I'm going to integrate from time 1 to 2, right? And now my power as a function, I'll say P of T dt has to equal the change in energy, E initial to E final, dE. And that's actually going to be equal to delta E, because this integral will be E final minus E initial, which is the change in E, which is the E dissipated, the electrical energy dissipated. So now I need to think, why did I use calculus? Right? I could have just done change in E because the current is changing as a function of time, meaning the power is changing as a function of time. Because in circuits, the power dissipated is I squared R. So if R is varying, which is not, right? If I is varying, which it is, I have to use I of T squared times R. And since R is constant, we'll just sub that out of our integral, and we'll say, because if I'm plugging in my P of T, right, this will take us here. I'll take. Now this integral becomes 1 to 2 I of T squared times R, which is a constant. dt has to equal the change, has to equal the energy dissipated. So now I'll take out R. What was my R? Let's see. My R was 2, 1 to 2. And I of T was, what was it? It was Bart. Yeah, Bart squared. So that was 0.5 was the magnetic field, and the area was also 0.5, divided by the resistance, which was... Oh, wow, the resistance actually cancels, I think. Oh, wait, no, it doesn't. Oh, it's because I forgot to square the current as a whole. I'll keep doing this symbolically. So that's our power. So now let's change this integral symbolically. I'll take out the R. Now I of T was B A R T squared dt. That has to become R, right? And if I square all of these things, I get B squared, A squared, R squared, T to the fourth dt. I'll take out all my constants and evaluate my integral. B squared, A squared, R. One of the R's will cancel, and I'll be left. Well, T is the variable here, so 1 to 2. 1 over T to the fourth dt. Now I'll just have to plug in the values they gave me for B. So it'll be 0.5 squared times 0.5 squared over, and what was that resistance? 2. And the integral 1 to 2, 1 over 4, or no, 1 over T to the fourth dt. And I'll just evaluate this in Desmos, because unless they ask you to integrate, when they ask you to integrate and they give you points for integrating, they'll usually just leave it symbolically. But here they're giving us numbers. So on the AP exam, we're not going to waste our time integrating, right? We're just going to run like the wind to finish the exam. Okay, so we'll do 1 over, and I like to integrate like this. I could have used dx, but I don't feel like doing that. So that means our electrical energy dissipated is that 0.091 joules. I'll say 911. There's our answer. Any questions? If you have any questions, just let me know. And that's what we need to do for that. Sorry for this video being long. This free response was actually really long. It took me like 50 minutes. I don't know why they would ask a question like this. It was honestly really hard. So the ring is then rotated so that the plane is aligned at a 30-degree angle in the magnetic field. As shown, the magnetic field is is reset to a magnitude b naught at time t and a new time t equals 0, and again begins to decrease according to this equation. The magnetic field begins to decrease according with that equation. And now they're going to ask us, will the amount of electrical energy dissipated from the ring, or energy dissipated from the ring from t equals 1 to t equals 2 be greater than, less than, or equal to the energy dissipated in part B? We're going to think, right? And we're going to say less than. The reason why it's less than is because the magnetic flux as a function of time is equal to B A B of t A cos theta. Less, or no, cos theta is max at theta equals 0, and less at theta equals 30. Therefore, the electric flux is less, and di flux, the derivative, if electric flux is less, the derivative and t, and there's a lot, and the current is less. Because if you have less current, then you have less dissipated energy, right? Because I have less magnetic flux overall as a function of time. I have the less of the derivative as a function of time, and I have less as of the induced current. Then I have less of the induced voltage. I have less of the induced current then, and then I have less of the electrical energy if I have less current. So there we go. So now a ring is mounted on an axle that is perpendicular to the magnetic field. The magnitude of the magnetic field is now held at a constant B naught equals 0.5 Tesla as shown. The ring rotates around the axle, and the induced EMF in the ring as a function of time is shown as the graph. That looks like a sine curve to me, but that's okay. Calculate the angular speed of the rotating ring in rads per sec. So let's think. Whenever we have this graph, the period, right? There's the period of oscillation, that's the time for one oscillation, is going to be equal to, whenever you have oscillatory motion, or I guess you could say just circular motion, harmonic motion, that's what t is. And I see from the graph t is 2 seconds, so I'll say 2 equals 2 pi over w. I'll cancel the 2's, multiply w to the other time, and realize, hey, w's pi rad per second. That's pretty cool. It's pretty neat. Bam, done. Calculate the maximum, or the magnitude of the maximum EMF induced in the ring, Emax. So they want us to find basically this one, these, because they're all the same value. So we're going to think, right? The theta, or the angular speed is in rad per second. Actually, I'll go to that later, but the induced is equal to the negative derivative of flux by Faraday's law, right? But now the ring is rotating, and the magnitude of the magnetic field is not changing. It's held constant. So that's going to equal the negative derivative of, well, actually, we'll derive the flux. The flux is equal to that B naught that they gave us times the area of the ring times the cosine of the theta between. But now theta is changing, right? Theta is changing, and we need to think, well, if W equals rad per second, then shouldn't W times time equal the theta? And the answer is yes, that's absolutely what it is. So the flux as a function of time, the magnetic flux as a function of time is now, and B naught is now, let's see, what was B naught? 0.5, and the area was still 0.5, great. 0.5 times 0.5 cos of WT, and what was W? It was pi. So it's actually 0.5 squared cos pi t. So now, if I do what I was doing here with Faraday's law, and I take the absolute value of the derivative of the flux, right, that will give me 0.5 squared, right, chain rule. sine of pi over pi t. And since there was no what's it called? Since there was no what's the word I'm looking for? Since there was no since there was the absolute value, the negative doesn't matter. In chain rule, right? I take the derivative of the outside, and then I derivative of the inside will give me pi, and then I multiply it. That's the new derivative. So here's our induced current as a function of time, and I know sine of pi of t maxes out at 1. So that means E of t has to equal 0.5 squared times pi. Meaning, that bothers me. 0.5 squared times pi is roughly 0.785339 volts. Bam. There's our max voltage. And you can also see even here that this maxes out when t is 1/2, right? So if I take sine of pi times a half, well, sine of pi over 2 is 1, it maxes out at 1, right? That's just logic behind that. So now let's think. This next question. The ring now begins to rotate at an angular speed 2w. On the graph below, draw a curve to indicate the new induced electromotive force in the ring. The dashed curve shows the electromotive force induced under original conditions. So let's practice. Let's think. So if t equals 2 pi divided by w, and this turns into 2w, right? Then the period has to half. The period has to half, right? If I give it a greater angular velocity, I increase this by 2, this has to decrease by 1/2. That's just factors of change. That's how that works. So now let's think. This whatever this completes here, now it's going to have to do in 1 second. So we're going to have 3 complete oscillations that look kind of like that. 3 complete oscillations. Next problem, or next issue. The magnitude of the max induced voltage will also change, right? So because if I were to just derive it without the pi, this would be 0.5 squared cos Wt. And that'll turn into 0.5 squared W sine Wt. And I know sine still maxes out at 1 no matter what. So if W increases by 2, then the max induced voltage has to also increase by 2 because this is proportional to that, right? If I multiply by 2 on this side, this one also has to multiply by 2 to account for the change because of the equal sign. That's how a direct relationship will work. So now that I know I have to have my period be 1 second and I have to reach this new height, right? I have to max out and complete an oscillation like this. The max induced voltage now has to be double what it was before. Then my graph will look somewhat like this, right? And you'll have to forgive my handwriting. It's kind of not good. But there's our graph. That's pretty much it. So now justify your sketch. This is pretty easy. T equals 2 pi over W. If W increases by 2, T halves. E of T has to equal BA W sine WT as earlier shown. If W increases by 2, max also increase by 2. Oh, and that's my sign graph looks horrible. And that's the 2021 AP Physics, Electricity, and Magnetism exam. Let me know if you guys have any questions, and excuse me for that voltage for that part 1. It took me a long time to get through it, and I apologize for that. Because I really like, I honestly don't get capacitors a lot, and I hope you guys could get it through my explanation, but I know I might have repeated myself a lot. Um, but really, I just hope it was comprehensive enough for you guys to understand. It's just capacitors I can understand. It's really difficult. It's really annoying. Um, and I personally, I myself find them really annoying, and I barely got through this section. So I hope you guys do well in your exams, especially it's April 26th. Only about 2 weeks until the AP Physics C exam. So yeah, good luck all you guys, and I hope you're enjoying your weekend.